So yeah, I think we are ready to get started now. Thank you everyone for joining this webinar from us here at SuperAnnotate. We're here today to talk about one-shot annotation and really some ways that you can speed up your annotation by quite a lot and really dive into how this works on the back end. My name is Leo Linden, and I'm a senior ML solutions engineer here at SuperAnnotate. So to start out, I just want to give a brief overview of what it is we are going to cover today. We are going to start by setting the stage for this discussion and dive into segmentation and what it actually is to ensure that we're all on the same page. And then I want to move on to talk a bit about the role of data and annotation in machine learning. Zoom out from there and have a look at the trends in the field and especially dive into foundational models and discuss after that a little bit about, do we still need old school data annotation, model training, and so on when foundational models are there? And I think the answer isn't entirely clear, but absolutely yes, I do. We still have a use and need for that. I'm going to cover a bit why. Then dive into really how these new trends coupled together with traditional data and annotation, and really how we can supercharge data annotation or data annotation workflows using generative AI and foundational models and a lot of those new techniques that are coming in that field. Then we're going to look a little bit into the future, see what is coming there. I'm leading here is saying it's customizable. We'll go into exactly what that is later on. And then we'll have a little bit of a wrap up and time for some question and answering on the end. So what is segmentation? Really, segmentation is essentially a computer vision task at its core, where we're trying to discover different objects within images. And this is different from object detection, that is basically finding just where an object is and what it is. So could be slightly similar to this first image here, the instance where these bounding boxes would be typical for an object detection algorithm. But in many cases, we're interested in more than just bounding boxes and where items are localized. We want to know more about them. What do they look like? What's their area? And so on. So the first type of segmentation is what we call instance segmentation. Here we're only looking at a couple of objects that we want to classify, localize, and identify. And you can see that in here, we distinct between different instances of the same item. We have other types of segmentation also. Of course, we have semantic segmentation. Here we're interested in kind of the entire image, breaking down each and every pixel and assign a class to that. But we don't make any distinction between different objects. You can see here, all the different turtles are treated as one and the same object in here. But you can also look at what's called panoptic segmentation, where we combine these two and really both break down the entire image, but also tries to segment each of these objects apart as well. So it is a high overview of different types of segmentation tasks and so on. Let's jump on to have a look at a few of those use cases where this is actually useful in the real world. One, we can start for segmentation, really classic segmentation is within infrastructure and manufacturing. We might be interested in detecting things such as defects, and it might be interesting to see both kind of size and shape and so on of these items, because the shape of a defect can have a big impact on how it should be classified or treated and can contain a lot of valuable information, which is why just object detection isn't always enough. Oftentimes, this is small objects. We can have very similar backgrounds. See, it's mainly a gray image here where we're trying to find some cracks in. There might be a need for a high-level expertise to actually understand what one of those is. And yeah, bounding boxes can be a bit too much noise and unnecessary area around this. Another use case for segmentation that many might have encountered a bit more than infrastructure and so on is within fashion, within e-commerce, within retail, where there are use cases where we might be able to want to detect and segment different types of garments people are wearing, for example, or other types of objects that are being sold, both to kind of, if you take an image, be able to kind of detect and show you, what product is this? Where can you find it? But definitely also in stuff like virtual try-on, where it's really important that you do segment these out. You don't want your virtual try-on garment to be on top of your hair. For example, you want your hair to go on top of the garment. And here, kind of separating all different components in an image is also really important. It might be a lot of labels, there might be a lot of overlap. And here we're really looking at that kind of panoptic or instance segmentation of different objects. If anyone is working more with remote sensing and similar, this is also a use case where we see a lot of need for segmentation. And why don't you use bounding boxes here if you want to detect objects? Well, in many cases, what we're interested in this type of data is both the shape of items, but also areas of different objects. This can be deforestation, it can be agriculture, it can be trying to detect different parts of a field that needs fertilizing or it's growing well, and things like that. So again, we're really interested in discovering different types of areas that are not uniform. And here, segmentation is again really important, but it might also be use cases such as mapping as well. Moving on, we also, of course, have autonomous driving, a use case that is always hyped in the media. It feels like we're getting a bit closer, but there's a lot of work happening here behind the scenes. So segmentation, again, of images, often more kind of really panoptic or just ordinary segmentation of every different piece. We might classify objects, but really general kind of want to separate them out into different types of objects as well. It's really important to discover people, cars, and not miss out on anything. Find out what is the drivable area. But there's a lot of nuanced questions as well, like how should we treat objects that are far away? What is really good accuracy in here as well? So that is an overview of different types of semantic segmentation and really why it's useful and why we should care about this. So from here, I want to jump on. I want to zoom out a little bit and talk about how we have in many ways entered a data-centric age of AI. And anyone who knows about Hugging Face or other sort of model hubs to this should feel quite familiar that models are quickly becoming a commodity. And the model architectures are open. You can download a pre-trained model and so on, or access it using a API. So with models just being a commodity, it's not necessarily new architectures and so on that makes a difference. What do, though, is oftentimes the quality of the data set, the content of the data set that you're using to train these models. And both oftentimes limit model performance and is the key to taking a finished model architecture, maybe fine-tune it, transfer learn it to a specific domain. And to many companies, when models really are this commodity, you can get the same model as anyone else, as a lot of competitors from these hubs. The data set you use to fine-tune and train that can be the key factor to building a competitive advantage. And here, really annotating data is the key. The data pipeline is becoming a main driver of time in data projects or ML projects when you spend less time on designing the actual model architecture. Boosting the data sets can be a way to increase performance, create more high quality data sets, or be able to kind of translate from big foundational models down to smaller models you deploy yourself as well. You need data because big kind of these commodity bundles are often really big. It takes a lot of computational resources. It can also be really relevant to dive into things such as model evaluation. This is, again, in a way, a new topic. When you build a model yourself from scratch, when you train it yourself on your own data set, you yourself is also sure about things such as, well, did you test on training data? Can I really trust that this model will perform well in my use case? And by building your own high quality evaluation data sets for your own domain, that can be a key to really be able to confidently select what is the best model and also try different models head to head that are out there and for yourself be sure that, yes, it does actually perform well on data I know was not in the training data set. And that's becoming especially important with models that are hold maybe behind APIs where you don't have any insight in what data they use to train that model either. So with data being more and more important for model performance, there is also a trade-off because gathering high quality data is really expensive. You'll have people sitting and labeling maybe day in, day out to collect data sets of thousands, tens of thousands, in some use cases, even hundreds of thousands of images to train your model and to achieve high performance. So there was a study a while back to look into the importance of label quality for semantic segmentation, because a natural question is, of course, well, how high quality labels do I really need to train a model? Can I sheep out and do lower quality, or do I really need the high quality throughout this entire data set? And what they find out was it's a bit of both. You can achieve quite high performance by training on lower resolution labels. What they did was essentially to label a large data set with very high, or actually they generated these labels using kind of synthetic simulated data. But then they really decreased label quality in a couple of different steps, as you can see in the image here. And up in this table, and as well as down in this graph, we can see how model performance as tested on this really fine-grained label data set was affected by different labeling errors or coarseness. So throughout, for each kind of level here, we do see that, of course, the fine labels have a pretty good effect on performance, but it's not that big once you increase the data volume. But more importantly, what they figured out was that you can actually reach higher performance than just a fine label if you go ahead and you have a very large data set of more coarse, low quality labels, and then in the end fine tune your data set on a smaller set of really high quality labels. You can see I used 48,000 of these lower quality labels and a fine tune on 1,000 of the high quality labels over here, or 3,000 of the high quality labels over here, and achieve high accuracy. So this is something that indicates that with data being super important, there are at least some ways to kind of scale down the time here. And if we can rapidly get a really large data set that is pretty decent, and then spend a lot of manual focus and effort on a smaller part of that data set to really, improve and fine tune and make that as perfect as possible, we can get really high quality models. We don't need the entire data set to be perfect. Worth noting here, though, is that even the coarse data set, it's pretty accurate. It's not completely off. So it still takes time and effort to build both the low quality part and, of course, the high quality part of this data set. So kind of with that in mind, that we do still need large data sets to train models, even if we can sheep out, so to say, on parts of that data set. I want to take another little step back and look at different trends in artificial intelligence here. We can see that in this Gartner hype cycle curve, I think a lot of you have seen this, especially throughout this year when we've had some really big advances within AI that has really reached the media, really gotten hyped very fast. But we start by looking kind of data labeling, annotation, computer vision here is really far out. It's approaching this plateau of productivity. It's technology that has been around for a long time. And then going back a little bit, what is hyped right now is really generative AI, foundational models. It's having a huge impact. It's solving a lot of important problems. It's definitely not just hype, but always a bit blown up. But what I want to take a look at here first is you can see both foundational models and generative AI are the hype. And out of these generative AI, most of us know what this is. It's the type of AI that can generate or create new creative content, often based on transformers or diffusers to create images or text data with algorithms such as stability that we see here, Midjourney, DALL-E within ChatGPT, as well as different sort of chatbots that we have as well, the more text-based aspect, like ChatGPT, Bard, Meta's Llama, Mistral, open source models. So it's a lot of happening here. But fantastic new innovations that all can unlock creativity and sparks new tools of uses for AI we previously hadn't considered, but as we'll see soon, they actually also have a lot of impact on how we do AI today, some parts of this. But this is generative AI. I also mentioned foundational models. That's on top of this hype curve as well. And what is that? Well, it turns out that a lot of these generative AI applications, they have these foundational models, so it's the under the hood. But they also have a lot of other applications that wouldn't necessarily be considered traditional generative AI. But the term foundational model was coined in a 2021 research paper from Stanford. And basically what this means is that these are kind of really big, oftentimes neural networks, deep neural networks, transformer-based, and so on, that are trained on a really large data set of labeled or unlabeled, semi-labeled data. Can be text files and documents in the case of the technology that underlies ChatGPT, or different image files and text combinations for promptable image generation systems. But the core is both that they're trained on this massive amount of data, but they're designed in a way that they're really adaptable to different use cases. You can generate a lot of different type of data using DALL-E for a variety of use cases, of course, but especially things like ChatGPT, you can really take that language core as well and use that for sentiment analysis or question answering or tons of other tasks that are out there. And with those being the most kind of well-known, those data generation, text-based tasks, there are actually a lot of other foundational models out there. We had a webinar a couple of months back around a foundational model for segmentation called Segment Anything. And this is a model that was developed by researchers from Meta Research. And it's specifically designed on segmentation. And this foundational aspect of being big and trained on a large amount of data really comes in here. It's trained on 11 million images and 1 billion different segmentation masks that they've gathered, and all really with the goal of creating something that is able to segment general objects. It doesn't have to be, a model that is trained just to segment emos and people as here, but really anything that is an object. And what is also interesting with this object or this model is that you can prompt it. It's like ChatGPT, DALL-E, and so on with points by clicking somewhere in an image, drawing a bounding box or a course label, or even a piece of text here, together with an image will generate these sorts of masks. You can see clicking here and different things or changing up, you get some different segmentation masks across this image. It's a pattern, the backpack, a part of the backpack, and so on. The architecture behind this model is, in many ways, pretty simple, but also complex. We start out with an image encoder that takes this image and really kind of compresses it down to a sort of embedding here. To that, we add either a prompt encoder, if we use a point or bounding box or text as input, or this kind of downsampler if there's a mask that is used as a prompt. This then combined with these image embeddings and a lightweight mask encoder or decoder here that then generate masks depending on what sort of prompt you put in. And what is really kind of clever about this setup is that even though it's a big foundational model, we generate these embeddings, we also have this lightweight mask decoder. So you can regenerate these embeddings for a large set of images and then go through and really prompt and get some of these segmentation masks created for you. So one question kind of naturally arises when we see foundational models such as this. Do we need this old school type of ML where we label data ourselves, maybe fine-tune a model on the labeled data and so on, when these foundational models exist? Isn't it possible to solve a lot of use cases by just having, prompting, a clever prompting system, and then we get everything we want with the text in and so on? And absolutely, I'm not going to say no. In some use cases, that might be exactly what you want, but the old school, so to say, ML or fine-tuning or training of smaller models definitely have their place still. It's adaptation and customization. So you might want to take this model and really fine-tune it, increases its performance and so on a specific subset of tasks. And here, then this sort of fine-tuning might be necessary, or training your own model. foundational models have quite a big computational load. In many cases, these are not things that you put on an edge device. You're not going to take entirety of ChatGPT and put it in your phone without an internet connection. You're not going to run a lot of these segment anything or image generation models on edge small devices, on construction sites, or drones flying around without internet connection as well. So a core use here is as well to be able to reduce the computational load. You can do it by training small models or context or kind of data distillation, model distillation, where you take kind of training data output from a big model, use it to train a smaller one. And another key point here is the question of ownership and competitiveness. A lot of foundational models are, again, as we mentioned before, really generally available as sort of a commodity to the entire market. You can download and run it, or you can connect to an API and so on. So ownership and competitiveness here can be important to have your own data in here, or to know you actually own this IP and this model for yourself. So with that discussed, I want to jump back to this hype curve as well. So while foundational models or generative AI won't necessarily remove the need for data annotation, data gathering, or model training, they do promise to greatly enhance the way we do data labeling and data annotation. So these items are not as separate as they might seem on this graph. They really do work very well together. And what we're going to dive into now is really how we can take this generative AI, the foundational models that are coming here, together with their previous knowledge from these studies, that we do still need large data sets, but maybe not everything completely manually annotated to create high quality models. So starting by segment anything, the foundational model for image segmentation. What we've done here is we've really taken this model and we've implemented this into our data annotation platform. Again, we had a webinar about exactly how we did that and so on that is on YouTube from a couple of months ago. So feel free to take a look at that one if you want to dive deeper into how this worked. But what you can do in the platform now is actually kind of pre-generates these embeddings, and then you can walk through and click on different items to automatically segment them, speeding up data annotation by quite a lot. But it's still not, the perfect thing. Still have to go through and kind of click on different items, decide what to annotate, go through every single item and do this. And that takes a lot of unnecessary time. So we really asked ourselves here, what can we do to make this even better? And the answer there lies in some parts of generative AI that isn't as apparent when you look on the models or in the foundational models when you look at their applications, such as shading or generating images. But really the core beneath all of this is mathematics and representations of data sets in something we call embeddings. We mentioned that a little bit in SAM. The first step is creating this sort of compressed representation of an image, but you can really do that for all different types of sources of data, different models, often these foundational ones trained on massive amounts of data to learn relationships, connections, different sort of attributes within your data set. So we have different objects here. On one side, these can be images, that can be text, it can be videos, or really anything else that we feed into this embedding model. Again, that can be one for just text or images. It can be something that is trained on kind of combined domain of text and images as well. And that will represent this as a vector, a series of numbers in some vector space with a lot of dimensions. There might be hundreds, or there might be even thousands of dimensions in this, where each of those dimensions or directions represents some sort of attribute. If we think about images, that could be, blueness or prettiness, or, likability for say persons or animals or anything like that. Coffee cupness, if we talk about items, so they represent all of them different aspects. And this is something that is being used a lot within chatbots and so on. You might be aware with ChatGPT suffering this problem with honesty. These are models trained to generate content, like make up content that seems likely. So sometimes they're right when you ask them a question, but not always. So here, a system that is called retrieval augmented generation is often used when you're interacting, say, with a database. A user writes some sort of query. that is being embedded to one of these vectors. And then we have a large knowledge base. An example could be you're talking to the documentation on a website. So this knowledge base would then be chunks of text that are also embedded. And by embedding this query, you can find corresponding pieces in this knowledge base that is similar to that, then passed up to this chatbot that writes an answer based on that knowledge. So we to ground that. But in the core of it, it's this search that is enabled by embeddings, a semantic search where you go through meaning of the text, style of the text, rather than keywords. So what we want to do is really bring this into images as well, or into our segmentation use cases. This is something we might be able to leverage. Some basic variants of this is being able to find similar images. It's kind of the first step. We've added this into our platform. You can go in, upload a ton of different images within a project, that we can select one of them and try to find similar. So the hedgehog there, using embeddings, it goes out and it finds everything that is kind of similar to a hedgehog within the data set. Using other models that are instead kind of trained on image captioning and kind of embeddings from that, you can go ahead and instead of clicking on finding similar here, we can write a text such as cows here. It will embed that and compare that to embeddings from all of these images to find anything that is like this little piece of text. So everything that is similar to the text cow. Find here a bunch of images of cows and then a couple of dogs that looks a bit like cows down there as well. And this is all nice and well, but how can we combine these? How can we somehow leverage embeddings and our little segmentation tool here to make segmentation a whole lot faster? Can we remove the need to be within one single image? Can we scale that? So what we do here, or what we think we can do here, and how actually implement, we'll have a look at that later on, is let's embed everything. Let's have Sam suggest every single possible embedding, or every single possible segmentation of an image. In this case, every single possible like Apple segmentation. But you can imagine if you have a huge data set of say 200,000 images and similar, run this SAM to find every possible segmentation of every one of those images, and then embed every one of those. And we get kind of this searchable database of all possible instances within the data set. So now we have something that we can go ahead and search. And ideally, if we now segment one item, we'll then be able to search over our entire data set to find everything else that is similar to that and try to segment that as well, removing the need to kind of one by one move through every image. So clicking over here, this is a little bit of an example here on what we call annotate similar, and kind of the end goal here as well. We've segmented this kind of Coca-Cola bottle here. Go ahead and press the annotate similar. It scans through every possible segmentation of your data set and then returns back, well, these are the other similar items that you found. Again, this is really object agnostic. It's not based on the model necessarily knowing what a Coca-Cola bottle is, but it's based on this kind of object agnostic segmentation algorithm together with these embeddings to find everything that then looks similar and segment that out. And another question here is, of course, this is a lot of data. I have personally tried to build an embedding search system on my laptop for text after about reaching, 10,000 different embeddings that really maxed out. Got a pink screen of death. I realized it's on Mac and not blue screen of death as on a laptop. So it's hard to do this on your own computer. But what we have done here, of course, is we've implemented this in quite an effective cloud structure, data structures. You can do this for data sets where you have tens of thousands of images to go through, generate embeddings for all these possible instances and really search through. So I'm going to skip this slide, and here we can see how this works. We'll wait for this to move back to the beginning, but here we have two segmented instances, a horse and a monkey. You click on one of them, it goes ahead and it finds everything else that looks like that monkey in the data set. You can select, gives you this sort of preview you're not necessarily sure just because embeddings are similar, it doesn't mean that it is the exact item that you're looking for. So you're getting to this preview window where you can easily manually scan through the dataset now, select which of these instances do you want to keep, which ones do you not want to keep, and then go ahead and annotate them. Of course, you can always go into one of these images as well and make any sort of manual adjustments to the dataset. But really our goal here is to enable you to with very few people, kind of supercharge the annotation workflow, so to say, to get to this large number of pretty good annotations very fast, and then go in and kind of manually refine a couple, a smaller subset of this to have a data set such as that one in the study where you can achieve a really high quality model, but really fast. And this removes a lot of the need that might be today to have people either go through and kind of manually click on each possible instance in your data set for each image, then go through and review. And that, of course, makes it easier than just doing it manually. But getting onto this stage can really scale that. So one person can do the work that it took quite a lot of people to do before, enabling you to leverage the power of these foundational models to rapidly create data sets that can be used to fine-tune much smaller models. And this is essentially a short little recap of how this comes together, leveraging the power of segmentation algorithms down here, combining that with embedding models to reach this sort of annotate similar, where we can now segment just one of these and then go ahead and find everything else that looks like that item through your data set. So this is kind of the now state, what we got, but this is of course not where this stops. The segmentation algorithm that is pretty generic, embeddings that is pretty generic are trained on kind of standard data sets, not necessarily fine-tuned to specific use cases. So where we are taking this within the following couple of months is really to enable two things. And here I've chosen to call them kind of bring your own model, BYOM, and continuous fine-tuning. So embeddings models can easily be fine-tuned on data set. Segmentation models can be adapted to specific niche use cases as well. And the ability to take these models and connect them into a platform where they're instantly scaled using high quality infrastructure. So you can do this sort of searching, embedding through everything at this large scale can really increase the performance on specific domains and use cases. And then down here, what we choose to call continuous fine-tuning is essentially that when you go through this process of finding similar items in your data set, you start by annotating kind of one item, you then go ahead and find all the similar items. You can approve everything that actually is correct, disapprove everything that is not, and then very easily, based on those results, kind of fine-tune these models to get higher and higher quality results each time you repeat this process, both kind of making your annotation faster and faster and faster, and also landing you with a good model there in the end. And then moving on here to just a little wrap up. So segmentation is a big use case that have applications across a wide range of different industries with the semantic segmentation, instance segmentation, panoptic segmentation that we've seen within both commercial use cases, within predictive maintenance, or remote sensing as well. And we then moved on a little bit to how data annotation still is important, maybe more than ever when the models are available to anyone. Then how SAM and other these open source AI models are implemented to make annotation faster, and how those coupled with embeddings can scale this even more. And really how those together here allow you to make annotation much faster and in the end, really fine-tune and create great models for your own data set. And there, I want to move over to questions if anyone have them. So feel free to like write any questions that you might have in the chat, and we'll make our best to answer them. I'm getting one question in here. I'm gonna select that to answer live. So are we using models that are okay for commercial use? And yes, we are. Everything in our platform is okay. It's built kind of ground up to support commercial use cases. When you create and annotate data in the platform, that is completely your property, the resulting data. And it is done using models that are okay to use for commercial use, that are released on kind of these maybe open source licenses, and also models that we develop and fine tune and create in-house to power this. Yes, we have another question here that I like to answer as well. So how do you use or extend the annotate similar tool to annotate multiple or many instances within a single image instead of finding images with a single instance per image? So that's a great question. I realized the example that we showed there, it was indeed kind of one instance per image. So this is not just for one instance per image. This covers a use case where you have multiple instances in the same image. You can go ahead, you can annotate one instance in one of your images. Then you can use this tool to find every kind of most of the other instances in your data set, be those in the same image, be that several from one image that look the same, and go ahead. So it's not limited to just one instance per image. We extract every possible instance from your data set using SAM or similar algorithms is used to really extract out every possible segmentation. And then these embeddings allow you to really search through that in your entire data set. And another question here that I think is really interesting as well is for a specific use case. So medical imaging, and if what we mentioned here can be applicable to medical imaging. So the answer here is kind of twofold. So for one, these models that are created, they are designed to be as generic as possible. So Segment Anything is able to find really anything that it resembles an object throughout the data set. And these embeddings allow you to find objects based on similarity. So there's nothing stopping them from being able to use on, for example, a medical imaging use case. So what can be a problem here is, of course, that these are not necessarily trained on data from that domain. So it's a very niche domain. It might be hard for the segmentation model, for example, to segment those specific items or specific things you have in there. But it might be hard for the embeddings model to encode that similarity. So that is really what we talked about in the end comes in, where we're moving over to both allowing you to bring kind of own embedding segmentation models. So this can be versions of the models we mentioned before that you have already fine-tuned and adapt in part to your use case. And that would make this process much easier. And also this kind of iterative fine-tuning process as well, where you can start out with a model that is pretty decent. You label a bunch of data. You might have to start out labeling data manually. Or you might be able to start out using this directly. And then you'll see a continuous improvement and be able to label kind of faster and faster as you go. And I think one thing that is important to mention there as well is that we never share any of the data you use with our models with any of other customers. So any interaction you have, say, with Sam and so on, is completely your own. Any kind of fine-tuning that is made on your version of that model will not be shared with any other customers as well. So for example, private data or sensitive data, you can rest assured that that always remains your own, and none of your work will be given over to any other customer within the platform. And another question that we got down here is how this relates to video data and image data. At the moment, this is available for image data. If you want to use this for videos as it is now, It's quite easy to actually upload a video in the image editor. It splits it up in different frames and allows for it to really encode those frames and then search through them. And then there are a lot of cool tools coming for the video editor as well. We'll be talking about in the future. And another question here, the reference images that was used to generate multiple instances, if that was annotated manually or not. So that one was annotated originally using the segment anything tool that is then used. And so if you open up an image in the tool, you can go ahead and you can click on instances, and using then SAM, it will try to segment those out from the background. Most cases, it does it pretty well. For example, horse, usually very easy to annotate like that. And then you can use that instance to search for similar. You can also do that using instances you segment manually as well. So you have full choice there. The accuracy of auto-generated annotations will depend a lot from use case to use case. And you really kind of have to try that out to get a feeling for it. So this is available in our tool. If you have it, you can start a new project and you can try this out, or you can reach out to anyone as a SuperAnnotate to see if we can set it up for you if it's not yet enabled. I think that is all the questions we have time to answer for today. I'd like to say thank you all to everyone for attending. We're going to be sending this recording out to all of you, and it's going to be available on our YouTube channel pretty shortly too. If you are interested in trying our platform out, or if you're currently a user that want to try this feature out, feel free to reach out to us. It's possible to book a demo and so on at our website, superannotate.com. Or if you're currently a customer, you can reach out to the support team or your account manager to hear more about this. Thank you all very much, and have a great rest of your evening or day, depending on where in the world you are.